Hey everyone, welcome to today's webinar. We're going to go ahead and get started now that we're at the top of the hour. My name is Kathy Hoverman. I'm moderating today's webinar from the Joint Committee on Fisheries Engineering and Science, a collaboration of ASCE's Environmental and Water Resources Institute and AFS Bioengineering section. Today's webinar is being recorded and will be available for future viewing on our YouTube channel. The series began back in 2015 to share information on aquatic organism passage, dam removal, fisheries improvement, community and stakeholder engagement, and related riverine topics. Since our inception, we've provided free quarterly webinars, with today being the very first in our 2026 series. The Joint Committee does do more than just this webinar series. If you're interested in learning more about it or becoming part of the committee, please feel free to reach out to anybody on our executive committee team. And then go ahead and check out what we do on our webpage at any time. We've got a lot of great information there. One of the things I want to highlight that is on our website, we do have some dam removal training resources. So this is on a technical level and as well on a management level. So great resources to find in there, especially if you are new or new-ish to the field of this kind of work with dam removals, with fish passage, with anything kind of in that related area. You can also find us on LinkedIn, where we hope to have conversations with you and about these topics. So feel free to drop questions in, start a conversation, and join us on LinkedIn. The 2026 Fish Passage Conference will be May 4th through the 8th at the University of California, Davis, strategically placed between Sacramento and San Francisco. The theme of the conference is Headwaters to Sidewaters to Estuaries, Improving Watershed Connectivity and Processes Through Restoration, Revitalization, Remediation, and Reintroduction. The abstracts have been closed and topics will be organized and announced in the coming weeks. There are several workshops and field trips on both ends of the technical conference. In addition to this really great agenda that's building up, the weather is typically sunny and warm. There's plenty to do and see around the area. So there's all kinds of great excuses for everyone to attend the conference and find something to enjoy in lovely Central Valley of California. The organizing committee has been working hard on this for several years now, and they are excited for y'all to come learn, share knowledge, and enjoy what they've put together. Associated with the conference are 2 awards that are given out. The nominations for these awards is closing very quickly. We have just 3 days left, and those nominations will be closed. This is for a Career Achievement Award, as well as a Distinguished Project Award. In kind of closing out some of these announcements, just want to give a quick thanks to my friends on the webinar task committee. And then also we've got a couple of options in the mix for our next webinar, but we haven't nailed it down yet. So we're thinking around May for our next webinar. And of course, we'll send out announcements once we have that locked down. For today's webinar, I was connected to our speaker today back in 2022 through Bob Guberneck when I was looking for data studies to show that stream simulation designed culverts really had an impact on resiliency. This is when resiliency really started to kind of pick up. And I wanted to talk about them to more to the transportation community and be able to talk about data and science behind it, not just fish and aquatic organisms, right? But have that kind of resiliency adaptation to it as another way to promote these structures. And so Dale was the guy. He was working on some stuff back then. And he gifted me some of the data and a draft of this paper that was published 3 years later in 2025. So I'm excited he's here today to kind of talk to everyone, share this information. that he worked hard to get published. It's a long road, long process, but it's great. I'm very excited to have him here today and share the paper with you all. So just a little bit Dale Higgins. He's performed a variety of hydrology and watershed management activities over the years involving streams, lakes, reservoirs, and wetlands until his retirement in 2018, where he then continued to work part-time, as a lot of folks seem to do in this field. He's been involved in planning, survey design, construction of over 250 road stream crossings to improve aquatic organism passage, water quality, channel morphology, safety, flood resilience, and reduced road maintenance. He's helped to teach many road stream crossing workshops in Wisconsin and eastern region of the Forest Service. Dale has also worked on hydropower relicensing projects, ecological classification of streams, river restoration, riparian management, and the development of monitoring of forestry best management practices for water quality. He's also very cool, been a consultant for water resources issues in Tanzania. So, whoo, Dale, you are a good man. This is great stuff. We're excited to hear from you. I'm going to stop talking so that Dale can start. So thanks a lot for being here, Dale, and excited to see what you have for us.
Okay, thanks, Kathy. I appreciate the intro and the opportunity to share what we have here. I'll go ahead and get started. Give me a second here. Hopefully I can get things arranged properly here. Okay, I think we're all set. I'll go ahead and get started. On July 11, 2016, northwest portion of the Chequamegon-Nicolet National Forest was hit with an extreme rainfall. And just so happened over the previous 15 to 20 years, forest replaced a large number of stream crossings in the area, primarily to restore streams and improve infrastructure. I like to say that the flood provided an unfortunate opportunity to learn about flood resiliency and adaptation to future flood increases. That opportunity evolved into this case study. It's been published as a general technical report by the U.S. Forest Service Northern Research Station. And I'd like to acknowledge that Dion Donner, who is the Assistant Director of Research and also Research Landscape Ecologist, the co-author with me on this. Okay, so I'll get started with a little bit of background. During the flood recovery work, we were able to attain peak flood flow estimates at 26 sites. 17 of those sites were designed using stream simulation process. Only one of those failed, although 13 overtopped. And at 9 other sites where we had flood flow estimates, 5 survived, 4 failed. So the peak flood flow estimates were estimated from high water marks and then hydraulic calculations. The calculations mostly performed using existing HEC-RAS models, which are also used to design most of the stream crossings. And I'll also be talking about the flood frequencies for each of the sites, and those were estimated from the 2003 U.S. Geological Survey Wisconsin regression equations. And here's Kathy showed this. Here's a picture of the publication. You can download it from this website. So objectives today, I'd like to sort of highlight and contrast the stream simulation versus traditional culvert design, and then briefly go over the results from the case study, including flood magnitudes we observed, culvert survival and failure and the lessons from that, identify how watershed characteristics affected flood response and implications that has for future flood flows, and then apply all those lessons to designing more flood resilient culverts. Okay, start out with traditional culvert design, usually referred to as hydrology and hydraulics, or H&H. It's a process where you determine a design peak discharge. Then you perform hydraulic modeling to select a culvert size that will pass the design discharge at an allowable headwater-to-depth ratio. So what's a headwater-to-depth ratio? Okay, this diagram will help illustrate it. Here's the culvert. the road fill over to culvert, and the water is flowing from left to right. And the water depth at the inlet of the culvert is the headwater acting on the inlet of the culvert. And then the depth is merely the depth of the pipe or the opening of the structure at the inlet. So in this case, headwater depth ratio would be 0.8. At the elevation where water would overtop the road, you'd have a headwater depth ratio of about 1.9. Okay, first step in determining the design discharge, the hydrology part of H&H, is selecting a flood frequency for the design. There are two common terms used for flood frequency. First one, annual exceedance probability, or AEP. I'll use that abbreviation some. It's a chance a flood will be exceeded in any given year, expressed as a percent, occasionally as a fraction. And the other one is a recurrence interval, or RI. That's the average number of years between an event being exceeded. A lot of people forget about this average part here. So the recurrence interval is just the inverse of the AEP fraction. So a 1% AEP flood is the same thing as a 100-year recurrence interval flood. Now, when considering traditional culvert design, one thing I want to point out is design standards, if they exist in some cases, vary by agency. So here are a few examples, typically using 2 or 4% AEP flood, which is, same as a 50 or 25-year flood. Headwater to depth ratios of somewhere between 1 and 1.5, although sometimes it can be the top of the road and a more frequent flood, depending on the agency and the type of road. So the one sort of shortcoming, I would say, with traditional H&H culvert design is that it tends to disrupt channel continuity, and in a lot of respects, it minimizes culvert size and installation costs, and doesn't really consider geomorphic characteristics of the stream, channel profile, sediment, or wood transport. So what this results in is culvert less than bankfull channel width, high headwaters usually have pretty frequent floods, upstream deposition of sediments, high velocities, culvert abrasion, and debris and other maintenance problems. These all lead to increased risk of failure. Stream simulation was initially developed to pass fish through culverts. It also results in extremely flood resilient structures. The basic concept is you design a stream channel through your crossing, and then you, figuratively speaking, wrap a structure around it. So there's 7 key requirements for stream simulation design. I've got them listed here. I just want to highlight 3. The first one, a single structure greater than or equal to bankfull width, alignment of the structure in a stream, especially at the inlet, and then a minimum hydraulic capacity with a headwater to depth ratio less than 0.8 at that 1% AEP flood. So that's provides quite a bit more capacity than the examples I just showed you. A few examples of stream simulation structures in northern Wisconsin. These two would be what we'd call higher gradient streams, greater than 0.5%. These are, more than that even. And then some lower, very low gradient streams, usually less than 0.5% streams that are really just moving sand-sized particles in organic matter. So what makes stream simulation so flood resilient? I have 4 factors here identified. And this graph illustrates the first 2. This is output from that HEC-RAS model you can use for designing culverts. This is the culvert right here, the road fill over to culvert, water flowing from right to left. This dark blue line is the 1% AEP flood, or 100-year flood. And you can see that at that flood flow, the headwater depth ratio is only 0.53, so well within the design standards, greater flood capacity. And then also in terms of freeboard, you can see at that flood flow, you have 2.5 feet of clearance or freeboard. Again, substantial flood capacity. So this site actually happens to be in the eastern part of Forest. It's not in the flood area, but I wanted to use an example and note that it occurs in an area that we would consider resilient to future flood flow increases. So I'll have more on that later in the presentation. Okay, next item is debris passage. A lot of structures fail because they plug with wood or other debris during a flood. So a study in northwestern California in 1990s in forested areas, they found that most wood in transport was less than bankfull width, but also that the wood longer than bankfull width tended to move parallel with flow, especially in the vicinity of a culvert. So their factors for promoting wood passage are also key requirements for stream simulation. Here they go, only one opening, no headwater ponding, no constriction, in other words, bankfull width or greater, freeboard, and then good alignment, especially at the inlet. So there's some illustration of that here, but especially the wood that's longer than bankfull width, you see the importance of alignment here. Your structure has a chance to pass that, not if it's not aligned at the inlet. So in the last one is abrasion resistance, traditional culvert design, no bed in the structure, no specifics about where to set the structure, dramatically shortens lifespan. Your failure typically occurs during high flow. So here's a pretty good example of that. This culvert here failed, was in a flood area, failed after being in the ground only 20 years. The white spots you see there may not be clear. Those are holes in the culvert. So this culvert was going to fail if the flood hadn't come in the near future anyway. Okay, and good example of abrasion resistance where you have bed and banks in the structure, and it greatly extends structure life. Okay, next I'm going to talk about the torrential rainfall and the resulting flood. The rainfall event started on July 11th, as I mentioned, lasted 6 hours. Yeah, large areas of the forest got over 5 inches of rain, and the hardest hit areas were in the 8 to 9 inch range. And if you look at the flood area here, the 6 hour 1% annual exceedance probability rainfall was 5.15 inches. Then the National Weather Service, after the event, did some analysis, and you'll see our flood study area right in here, and they concluded in that area that the rainfall event was at least a 1 in 500 year event, and in some cases more extreme than a 1 in 1,000 year event. So pretty extreme. So this map here illustrates kind of the rainfall within our area. And so this line here, 5 inches of rain, 6 inches, 7 inches, and it loops around to 7 on this side. And then we have 8 and 8, and then 9, 9. So large area with more than 8 inches of rainfall. The map also shows our sites, our 26 sites where we made flood flow estimates here. And then I guess you call them magenta lines show the watershed boundaries. Okay, so what flood peaks were caused by the rainfall event? First, just a little bit of background information. The 26 sites are watershed. Our drainage areas range from 0.21 up to just over 20 square miles, although most were under, say, 7 square miles. The actual peak flows were anywhere from 45 up to over 3,400 cubic feet per second, or CFS. So one of the first things we did is we took these flood flows, we divided them by the drainage area. So we standardized it in terms of flow per unit of drainage area. And you'll see we had this wide range from less than 25 CFS per square mile to over 1,700 CFS per square mile for the peak flood flow. And the fact that there were differences wasn't so surprising, but the magnitude of these differences, I think, what really caught our attention. And this led us to the concept right away that characteristics that lead to rapid runoff, those areas are more likely to see increased flooding from more extreme rainfall in the future than those areas that have more attenuated runoff. So how extreme were these flood flows? Would you believe me if I tell you it was a 20 million year flood? Well, how about a 300,000 year flood? How about a 10,000 year flood? Well, probably not. Okay. So where did these crazy numbers come from? Our best estimate of the flood frequency at each of the 26 sites, as I mentioned before, were the USGS regression equations, which were used to design most of these stream simulation crossings. Equations provide flood flow estimates for several AEPs, going from the 50% all the way up to the 0.2%, or if you want to think of it as a 500-year flood all the way down to the 2-year flood. So, well, one thing you can do is take these points, plot them on a log scale, and generally linearize it. So here, if you take the upper part of this line and extend it out to the 2016 flood, 365 CFS, come on down, voila, 300,000 year recurrence interval. So, aside from using this as sort of a cheap attention getter, I guess, why present this now? So, a couple of reasons I guess I have, and one is it really illustrates how extreme a flood, how an extreme flood, I should say, how much higher it can be than the traditional discharges you use for design, which would be down here. I think it also illustrates the fact of either the unreasonableness of trying to estimate flood frequencies beyond about that 0.2% AEP. And then just illustrates the problem of trying to characterize an extreme flood. Okay, so the flood frequency curve, though, I think is also useful from another standpoint. And most of you probably know this, but the public may not. If you deal with the public a lot, and that's that, a lot of times if you say, oh, we have a 1% or 100-year flood, or we have a 50% or 2-year flood, they might think that the 100-year flood would be 50 times greater than the 2-year flood. Well, in fact, that's not the case. It's not a linear relationship. So in this case, that it's about 3.9 times greater than that 50% AEP. So, it's good to keep that in mind. And then, interestingly enough, if you look at the 2016 flood, 365 CFS, it's about 4.2 times greater than 1% flood estimate. So how many of you would design a stream crossing to pass the 300,000 year recurrence interval? Well, nobody, right? Okay, so how about a flow that's 3 or 4 times the 1% AEP? Well, probably not. How about designing a structure using stream simulation procedures, then checking an extreme flood flow to determine if you could enhance survivability if such a flood would occur? If so, would you do it at every crossing, or would you do it at select crossings? Okay, so aside from presenting the peak flood flows in terms of flow per square mile, we also determined the ratio, the flood flow to the estimated 0.2% and 1% AEP floods. And we looked at this as a simple, informative way to express the extreme nature of the flood. So I've just got one of these highlighted here. It's the ratio to the 1% flood. And if you kind of ignore the 2 highest and the 2 lowest, they're basically in the range of 1.2 to 9 times the 1% flood estimate. So pretty substantial, pretty extreme flood. So the value of having all these peak flood flow estimates, which I consider rare in post-flood studies, especially regarding road street crossing, they provide a proper perspective for the flood flows in comparison to design criteria. And also they give you insight into the variability of runoff that can occur across a flood area. Most extreme floods are characterized only by a single rainfall amount or possibly a nearby USGS gauge, but they don't really take into account this spatial variability that can occur. Okay, so next I want to talk about the structures and what survived and what didn't, and why. And I'm going to start off with what I'll call the other designs, and this will include not only the few we have flood flow estimates at, but a lot of other structures that failed. And here are 2 examples of those. And the first thing I say is everything pretty much failed because it was such an extreme flood. But beyond that, a lot of the non-stream sim culverts were undersized and would have failed at much lower flows. Here are these two examples. And I have constriction ratio showing here. And what that is just the culvert width divided by the bank full width. So you can see that they were substantially less than bank full width, which is undersized from a stream simulation standpoint. And you can see they failed catastrophically. So another site here, undersized, 58% of bank full width. There's a culvert there. It got washed quite a distance downstream from the road crossing. We did get a flood flow estimate there, 10 times the 1% AEP. So an interesting thing about this site is that it had, compared to some other sites, and there were others like this too, narrower floodplain, steeper channel, had a pretty high road fill. And that led us to really start thinking about how those factors might affect survival and failure, because they really can create greater hydraulic forces, increase the potential failure, especially if the road overtops. So, and so one of the things we did is thinking about the floodplain or flood-prone width, you can use entrenchment, which is really the flood-prone width divided by the bankfull width to characterize how narrow or wide your floodplain is. And so that's a common measurement. We use that later in the presentation. So, okay, some of the stream simulation designs, I think I'll start out just focusing on just the value and the capacity that bankfull width structures provide. Here are 4 different structures. They all survived the 2016 flood with no maintenance required. 3 of them overtopped slightly, and they survived floods that, we estimate were anywhere from 1.6 all the way up to 4.9 times the 1% AEP flood. So a couple more sites and try to highlight a little more here. In addition to the bank full width, a lot of the structures overtopped because of the extreme nature of the flood. And in these 2 cases, the one on the right survived a flood 4.1 times AEP flood. Really not much maintenance needed, but large or broad flood-prone areas allowed water to come over the road over a wide area, and that no doubt helped survivability. In this particular case, survived 2.5 times the 1% flood. You can see that part of the road gravel washed off, a lot of it deposited right in the ditch, but the crossing survived. So you did need some maintenance work there, and that happened at about 5 of the sites, I believe. So another example with the slight entrenchment overflow, and actually 2 points I want to make with this slide. And so here this crossing is constriction ratio, under 0.6, failed a couple times in recent history. Here it is, 2013 failing. Bankfull width structure set at the proper elevation in 2014. It survived the 2016 flood. 6.5 times the 1% flood. But there was some loss of gravel off the road to one side of the structure. So 2 of the factors I want to point out here again is that HECRAS model, culvert, the road fill, water's flowing from right to left. This dark line is the 1% flood, the 0.2%, the fine line above it. One of the things you see is, well, of course, headwater depth ratio 0.7, 1.5 feet of freebird, so lot of capacity. You also see that there's no increase in headwater at the 1% flood, and that the tailwater can rise with the headwater to get up to the top of the culvert. Then they start to separate. Here's the 2016 flood, come over the road off to one side. But I believe part of the reason these structures are all surviving is because the tailwater can come up a lot higher, and the head difference at road overtopping is a lot less. So I think that helps explain some of it. Here is that same site in cross section. The other point I wanted to make is installing a bankfull width culvert embedded below the stream bed, still have to usually add fill to get minimum fill over the culvert. In this case, this is the post-construction road, created a low point off to one side of the structure. And even though the peak flood level got up to this area, the flow was concentrated over here, lost some gravel off the road, but the structure survived and the road only needed some moderate maintenance. So, and with these broad flood prone areas, it's actually ideal if you can get two overflow areas. So here's another example, the pre-construction road, 3 small culverts that had failed repeatedly. This was installed in 2012, bankfull width culvert, new road ramps up and over, creating 2 overflow areas. That's exactly what happened during the flood. Each side lost a little bit of gravel. You can see a little bit in the ditch here. Here's the vehicle down there. The town road crew had been through and graded already, so you don't see the loss of gravel off the road surface. But again, these slight entrenchment, broad overflow areas, bankfull width culvert to help these structures survive very extreme flood. Here's an example of a site, higher gradient site. Greater bankfull width culvert was installed in 2007. Bankfull width 8, 12.5-foot culvert replacing a less than 5-foot culvert to allow room for stream bed banks in the structure. This site had a flood flow of about 2.2 times the 1% flood. This site actually overtopped, and you really don't want that to happen because you can lose your bed material. And in fact, some of the bank rocks bed material was lost. But we think these large key pieces of rocks, vortex rock, help to maintain some of that material and still providing fish passage. So I also like to make some comments about overtopping here. The road, this substantial capacity here, even though the road overtopped, only about 9 or 10% of flow went over the road, but it was at the peak, 1/2 foot deep, 130 feet wide. So this is in a narrow floodplain. The floodplain is only 19 feet wide. So the point I want to make here is that it is possible to pass a portion of extreme flood over the road, but in a more entrenched stream, but it's probably going to occur right at the structure. And so in this case, the road was paved. We have good riprap dense vegetation. No doubt that helped survival of the structure. And the other thing I want to point out is if this happens on these more narrow floodplains, you got to make sure that there's a little bit of high ground on each side. So when it overtops, the flow does not go down the road and take out a 1/2 mile or 1/4 mile of road. We call that stream capture. So you have to be very careful about that. Few additional points I want to make regarding survival at overtopping. This was a stream simulation structure, a lot of capacity, good vegetation, riprap. This was one of the more extreme floods. Almost 80% of the flood passed over this structure. I think the vegetation in the road, it's a low volume road, helped survivability. Here's another crossing. This was not a bankfull width culvert, but it was installed in about the mid-90s. It passed about 70% of the flow over the road. You can see the dense vegetation here, large riprap. Flood flow was 3.3 times 1% AP. No doubt those all added to survivability. So a couple last points, just in general, our observation was that, concrete structures are strong, massive, and they're pretty resilient, even in the face of failure. And so, here's an example of a concrete bridge. Flow got over the road. Bridge survived. We did not have any flood flow estimates here. The only thing with the bridge is there's a little scour under the abutment, so it needs some maintenance. But one thing that probably helped this structure is its 20 feet wide bankfull width was 16.5. So it's actually greater than bankfull width. So I'm sure that aided its survivability. And then this stream simulation structure replaced a culvert, a 30-foot bridge replaced a culvert. Road was paved. The flood was 2.4 times 1% AP. And the water came actually just over the top of the railing here. You can see the log that was deposited. It's a wooden bridge, but it's set on concrete footers tied into bedrock. This is an area where there's shallow bedrock. So amazing survivability. The road actually held in place pretty good by the pavement, although a little bit was lost there. So a few words about, I mentioned we had 13 stream sim sites flow over the road. One of the other sites, and they were kind of, there was a lot of variability in the amount of flow. So 4 sites was a minor amount, I would say, in the, the 10% range. Another 4 sites in the moderate amount of water from this extreme flood going over the road, 50%. And we had some that were in that 70 or 80% range. And a lot of it, it kind of correlated with the extremity of flood, but not entirely. A lot had to do with, the individual site characteristics. This is some of the output from HECRAS or flow over the road. Mean depth, half a foot, but quite a bit of variability depending on the site. Maximum depth of a foot, again, variability. Average width, 180 feet, wide range again. And then mean velocity is about 2 feet per second, varying from about 1 to over 3.5. So next I want to talk briefly about this idea of the site and or valley factors and how they may affect survivability, especially at overtopping. So these graphs, 2 graphs here, and I want to make 2 points with them just to show kind of the range of our data for our 26 sites. So we have entrenchment down here on both graphs. And you can see entrenchment goes from 1.2 all the way up to the mid 70s, although the vast majority were less than 45. But these are all pretty slight entrenchments. Channel slope from 0.1 all the way up to 3.2%. And then road fill height here, anywhere from about 2 up to 12 feet. And we went from the low point in road profile near the crossing down to floodplain level. So the other thing I mentioned earlier about how these 3 tend to interrelate. And so the graph provides a good example of that. So you look at entrenchments greater than 7, and you'll see that all the slopes are pretty much, from 0.1 to 0.4%. And it would make sense. These are broad flood-prone areas. Predominantly, you have a stream flowing through a wetland. And then as entrenchments start to get less, and all of a sudden our slopes go from 0.5 to 3%. And actually, if you get down to entrenchment of 2, we have our 5 highest slopes ranging from 1.5 to 3.2%. And then on the, with regard to road fill, kind of same thing, entrenchments greater than 10, that's where all our 2 to 4 foot fills are. So you broad flood prone area, wetlands with the stream, and low road fills. Then as entrenchment starts to get less, we start going from fills of 4 to 8 feet. And then if it gets, less than 5 or 6, then we're up in that 8 to 12 range. So we have a few general guidelines here for, classifying a site to vulnerability, especially at overtopping, just 2 broad classes, but with a gray area in between. So these are general guidelines based on our sites and our observations, some of our data. And keep in mind, they're mainly for areas less than 10 square miles, drainage areas. And we suggest use professional judgment, classifying the intermediate areas, and refine these things with your own local knowledge and experience. So summarized kind of the survival and failures, and focus mainly on the survival. Stream sim design provides substantially greater flood capacity. None of the sites became plugged with debris, and that aided their survival. Broad flood-prone areas provided substantial flow over the road to these extreme floods in many cases. And then at some of those sites, the road ramped up over the structure, allowing overflow on one or both sides of the structure rather than directly over it. And, construction maintenance practices that provided good erosion protection certainly appeared to help survival at overtopping. Okay, so next thing I want to do is talk about watershed response to extreme rainfall and implications for future increases in flood flow. It was immediately apparent that the substantial variation, we saw in flood response correlated with landforms and individual watershed characteristics. So this map shows again our 26 sites. Only this time we got them color-coded by their flood flow class, red being greater than 1,000 CFS per square mile for the peak flood flow, green is less than 60. And so the map shows those. It shows their watershed areas, and then it shows underlying land type associations, or LTAs. And those are ecological units based on topography, surficial geology, soil families, and some other factors. But those factors all correlate closely with hydrologic processes. So I think at this point, I'd like to reiterate again, the substantial differences in watershed response drove home that point that watersheds that produce more rapid runoff are likely to see greater increases in flood flows from extreme rainfall in the future than those that tend to attenuate runoff. So, and then the other point is we wouldn't have been able to observe those broad differences if we hadn't been fortunate enough to get so many peak flood flow estimates from the flood. So let's look at this in a little more detail. First land type association, Pinocchio-Gibbik, Iron Range is dark gray area. It's an area of shallow silt soils over bedrock with steeper slopes, more entrenched streams, less storage capacity, and it produced the highest flood peaks. And you can see those here, the red, the magenta, and with the vast majority over 600 CFS per square mile. If you go down to the Valhalla Marinesco Moraines LTA, this dark brown area, you can see that it had the sort of the next highest flood response, with flood flows mainly in that 100 to 200 CFS per square, 500 CFS per square mile range. And then we go down to this Chequamegon Wash Till and Outwash complex here. The Glidden Drumlins, which included just one watershed, and then Cable Rolling Outwash over here, which included one watershed. They had the least flashy runoff, I would say, with most of the flood peaks less than 250 CFS per square mile, some substantially less than that, less than 60 here. So let us the idea that let's look a little closer at LTAs, and to do that, we classified each watershed area for site by their dominant LTA. Some were, a complex of two, and due to lack of replication, we combined them into three groups that were relatively similar, and then performed some statistical analysis. The mean differences for the three groups significantly different, but we also had rainfall estimates for each watershed, and they were different by almost an inch, from 7.5 up to 8.5 inches. So using regression analysis, peak flow on rainfall for each individual group, we were able to use that as a covariate and adjust the mean peak flows for each group to factor out the effect of rainfall. Still had a statistically significant difference. And then, but the eye-popping thing to me is, the means 50 CFS per square mile to 250 to 550. So, and related to that, so we felt like LTA is doing a good job to characterize flood potential and runoff. And then a good example of that is two sites that had nearly identical rainfall. So we have site over here in that Cable Rolling Outwash, 8 inches of rainfall, 27 CFS per square mile. Go over into that Pinocchio-Gibbik area, 8.08 inches of rainfall. So I'm nearly identical rainfall, 220 CFS per square mile, or more than eight times greater than this site for the same rainfall. So much flashier, much more responsive. So it was clear to us that the watershed characteristics, as characterized by LTA, had this strong correlation with flood response. So the next question was, well, how do we extrapolate that knowledge to classify the vulnerability or resilience of areas to increases in flood flows from more extreme rainfall outside of the flood area? Okay, and so to pursue that idea, we looked at 4 variables, and 3 of these are used in the USGS regression equations. So we regress main channel slope, peak flow, significant relationship, storage on peak flow, significant, declining relationship, saturated hydraulic conductivity, statistically significant relationship. And then we also use drainage density. And so all significant related. So we thought, well, we can use a few of these variables or to help classify LTAs was the idea. But we also looked at how they interrelated. So here's main channel slope in storage, good relationship. Main channel slope, drainage density, storage and saturated hydraulic conductivity, and then drainage density. So this told us, because of their interrelationship, that we could use just a few of these variables more than likely to explain the same amount of variability. So this led us to the idea that we could use storage drainage density along with the LTA descriptions and the U.S. Geological Survey gauge data, classify the vulnerability of land type associations in Wisconsin to increases in flood flows from more extreme rainfall. So the steps we used are outlined here. I'll go through them briefly. So step one, determine storage and drainage density for each LTA in Wisconsin. It's a GIS exercise. Get lakes and hydro layer, lakes and ponds, wetland layer, determine storage in percent for each LTA, overlay the stream layer with each LTA, determine drainage density, miles per square mile. And we obtained USGS gauge locations, their associated 1% flood flows from their frequency analyses. It was a shapefile of points. And then we only used the sites that had drainage areas less than 75 square miles and that were unregulated, so be more natural flood flows. And then we also divided flood flows by drainage areas, so we could look at unit area flood flows, plotted them on the map, summarize the data. So basically in a spreadsheet, summarize them, calculate some indices, sorted them, and then basically use professional judgment guided by the data and LTA descriptions. And we placed each LTA into one of 4 vulnerability classes. And so here we are. Here's a look at what the data looked like. Drainage density went from 0.6 for resilient up to over 2 for vulnerable. If you look at storage, for moderately resilient, greater than 25% storage, down to 6% for vulnerable. The resilient areas are a special case because they're predominantly groundwater recharge areas. High infiltration rates tend to have less storage, so we took that into account during the classification process. And then looking at USGS unit flood flows, resilient areas, median 14 CFS, about 40 for moderately resilient, moderately vulnerable, about 90 CFS per square mile, and then 300 CFS per square mile for vulnerable. And this is what the map looks like for the state. Blue are the resilient areas, again, predominantly groundwater recharge areas, high infiltration rates. You can see flood flows less than 20 CFS per square mile. Early in the presentation, I showed that one example of that site in the eastern part of the Schwalm-Nicolet National Forest. That site was located right here in this resilient area. And then you can move to the green areas where classified as moderately resilient, somewhat higher flood flows per unit area. Yellow, moderately vulnerable, and then the red, vulnerable. They tended to be the driftless area, the Lake Superior clay plain areas of less storage. And one thing I wanted to point out here is this map, both Shapefile and Geodatabase, has been published and it's available online at this location. So just a couple more points. Go back to Northwest Wisconsin flood area here. All 4 of the vulnerabilities are showing. So here's the blue. I want to demonstrate the reduced drainage density. Storage down here are dark blue areas. less storage in these groundwater recharge areas. The green, moderately resilient, again, a little bit higher drainage density, lots and lots of storage in these areas. And then you move into moderately vulnerable. This is that Pinocchio-Gilbeck area, higher drainage density, less storage, another piece of bedrock controlled topography there. And then the vulnerable areas, very high drainage densities, less storage on Lake Superior Clay Plain. So try and wrap this up. What are our advice or conclusions? Use stream simulation as a baseline for flood resiliency. Then use the LTA vulnerability classes, if you have it. If not, you can go down to a specific site you're going to design, do your site survey, hydrologic assessment, stream sim design, and then you can determine from your hydrologic assessment, hey, does the vulnerability need to be adjusted? Or if we don't have it, can we estimate a vulnerability? Use your survey data to determine your site valley vulnerability. And then you use those two things to determine if depending on the vulnerability, do you want to supplement any design features for your stream simulation design? So here's a flow chart describing the process. Use stream simulation design standards as a baseline in all cases. Resilient watershed. It doesn't matter in the site. Need for additional features, probably not likely. Moderately resilient site, watershed. Resilient site, easy to provide overflow areas. Probably want to do that. Get down to a vulnerable site, you have to decide, what is the risk of extreme flood or increased flooding in the future? Do I need to harden an overflow area or do something like that? Moderately vulnerable watershed, definitely got to provide overflow areas. Consider increasing structure width. If you're on a vulnerable site, you may need to harden a downstream area, and so on. So as you move in this direction, you bring these forward, but then you add in things. So vulnerable watershed, you might want to use a more conservative flood flow estimate. You may want to increase structure size. You may want to go, for example, to bridges or concrete structures, raise them up. So we've got a variety of things listed here. So with that, I'm hoping to end. I just want to point out a few references. This is the stream simulation design guide. It's approximately 600 pages, just packed with all kinds of good information on stream simulation design. Either one of these, you could cut and paste either one of these into your web browser. You should be able to download that. And then I have a couple other references I want to point out. Here is the Wisconsin Initiative on Climate Change Impacts has working groups. The infrastructure working group had a stream crossing committee that produced a flood resilient culvert design primer for Wisconsin. It's about 10 pages, nice summary. And it basically is a stream sim summary, but just focusing on the flood resilient aspects and some specifics like, low gradient streams in Wisconsin. So that might be handy. And then it also has a companion manual, much bigger, goes into much more details, probably 100 pages, lots of different examples, survey and design. But in the hydraulics section, not only does it provide a variety of different analyses, but it shows like how to do your headwater depth ratio, but also how to model, how you might be able to model an extreme flood. The one point here I want to make is in HECRAS, you have to have bounding cross sections right above and below the road, and the road profile. Try to have a common point so those line up well, and then make sure they extend out either way so you can encompass the largest flood you'd like to model. So to download these structures, you can go to the Wiki Infrastructure Working Group here, and then you page down, there's a link that says Flood Resilient Road Stream Crossings. That'll open up a document that has links to each of these. And so with that, I think I will stop. And let's see.
All right, Dale, that was amazing. We have tons of questions in the chat. We are not going to even come close to being able to hit them. So what I want to ask before we try to hit, well, look, some great applause. Is it okay if people contact you if they have some additional questions?
Yes, sure. And
Okay,
let's
I'm going to
see.
put your email in the chat then for anybody who
Okay,
wants
great.
to email
Yes.
you. Does that
Yep.
work?
Be,
Okay.
more than happy to try to answer any questions I can.
Okay, perfect. Okay, so let's maybe ask a couple of these questions, see if we can get a few of them answered before we have to go. I have 4 minutes on the clock here. All right, so first one, how often are terrestrial wildlife considered in the designs of AOP connectivity projects? Any low-hanging, cost-effective design recommendations for being able to improve terrestrial and aquatic connectivity?
So my answer to that is, really the design is an interdisciplinary process. So like in Forest Service, I was hydrologist, work with civil engineer, and then the fish biologists, the recreation people, hydrologists. So some of that depends on the setting and the issue. If I can go back very quickly, take me a few seconds here. Oh, here we go. Okay, so if you look at this site here, this was over a highway and we worked with the DOT, but you'll see these banks here were built with mostly with rock, but then there was gravel put in there and consulting with, in this case, the Forest Service was involved, the local tribe was involved, the DNR was involved, and they wanted terrestrial passage. And so we're afraid with large, rocks that the deer might have trouble passing through there. So that was actually filled in with fine gravel. And what you see now are organic deposits over bank flows with organics depositing there. But there was a case where you didn't want to send animals up over the highway, be a killing field, so to provide terrestrial passage. So I would say it varies from structure to structure, depending on the traffic, the height of the fill, the wildlife concerns and all that, but it certainly should be considered. It's a good question.
Yeah, that's great. Okay, and there's also another answer within chat if folks want to make sure they read some of that as well. There's some more information in there. Dale, a couple people would love to have a copy of the presentation. I will say, folks, get the paper. Get the paper. Dale, if it's okay, we could also put this presentation on our website. But again, the YouTube video will also be available. So
Okay.
there should be a couple different resources for folks to check back on some of this great knowledge. There is maybe time for one more question here, and then the kind of the next one on there is about your peak flow spreadsheet. Is the peak flow spreadsheet used often, or is it just for this study? It's a good detailed snapshot of flooding.
Oh, you mean like this one here? Is that?
Yeah, I believe
Yeah,
that's
so
what
this
it's
was
about.
just for this study. So, but I mean, any crossing you design, you're going to do your flood flow estimates, you can do your hydraulic modeling, so you do that site by site. But if it also pays to be familiar with the surrounding USGS gauges and their flood flows. That's why I like to do the flood flows per unit area, because it gives you some sense of like how flashy or the streams are. One thing, you do have to be careful with unit flood flows, though, because as drainage areas increase, flood flows will go down because of attenuated flow and all that. But if you keep it to a fairly narrow range like we did here, I think you're okay. So, but that's one thing to think about if you're looking at gauge that's 1,000 square miles and you have a 2 square mile watershed, especially with peak flows. Average day flows maybe not quite so bad. So I don't know if I answered the question, but anyway.
I think that's great. Hey, let's scoot this one last question in. I think it's a really interesting one. Was stream simulation used to fix the culverts that failed? But also, I think here's maybe the interesting part. Did the nearby county and state roads have similar failures, and what was their response? Can you knock that answer out in a minute?
I would say that the structures that failed mostly It's complicated because we worked with Eastern Federal Lands from Federal Highway Administration, and they aren't all bought in on StreamSim, but we got bankfull, and I retired, and the people behind me, Jim Minot, the hydrologist, he worked with them and got bankfull with culverts. So I'd say the basic answer is yes, we got it, although they had to go back in and tweak things a little bit. Let's see, was there another part to the question?
The local community, what was
Oh,
their response?
their, you know, I mean, their response is, get the roads open, and they worked with FEMA, so I can't really answer that completely. I guess I think, wherever they could, they try to put in a bigger structure, but that's not always the case with it's replacing kind, which is usually
Yeah.
structures are undersized. So yeah.
Yeah, indeed. All right, Dale, we are going to have to cut it off here, folks. Thank you so much for attending. This is it's a great. I'm seeing 268 folks on this call. There may have been a little bit higher number at some point. Great work, Dale. This is just a supreme paper and information. So thank you so much for being here. Thank you everyone for attending and for throwing your great questions into the chat. I'm sorry we didn't have a chance to get to more. Please send Dale an email. Sounds like he's happy to talk. Thanks, everybody.
Okay. All right. Thank you.